In what matter? RF system. Okay, when? Tomorrow? Today. Okay. Okay, in any case, the question was, now we continue after the introduction of the concept of photon and the quantum, the quantization of the field. We ask what type of noise affected the optical communication system. So in other terms, if we consider optical communication signal, what type of noise could invest the transmission system, that is the transmission from transmitter to the receiver? And this question is fundamental in whatever is the communication. Because we need to answer to this question in order to evaluate the signal to noise ratio. So the more general treatment of the noise consider a situation of the black body. Black body is a collection, by definition, is a collection of oscillators, and these oscillators are exactly the harmonic oscillators that we introduced, in equilibrium with the radiation emitted by the oscillator itself. What means equilibrium? Equilibrium in thermodynamic sense. That is, equilibrium means that you reach some balance between energy supplied and acquired by the oscillator itself. This equilibrium means that we have a stable amount of electromagnetic energy inside this cavity. The cavity contains this oscillator. And we call this system, that is by definition, I repeat, the connection of the oscillator at the equilibrium plus the electromagnetic radiation at the equilibrium. That is, the system is made by two components, one electromagnetic oscillator, one electromagnetic radiation, and one connection of oscillator, black body. Okay? So this is by definition the black body. Now, we study the black body in order to understand the noise. I provided you some word taken by Planck itself when he described the oscillator. That was not quantized at the time of Planck, but however considered an abstract entity. So Planck said, hence, for the investigation of the properties of the state of black radiation, so black radiation, remember black body, in fact, okay? So he used the term black radiation because it's the nature of the bodies which are assumed to be in the vacuum is perfectly immaterial. Material means that it's not important, it's not really important, okay? So we talk about, also Planck talked about a vacuum, okay? Why vacuum? Because imagine that this black body don't contain more than the oscillator, that it don't contain gas or other artifact that could change the absorption property, okay? In fact, it does not even matter whether such body really exists somewhere in nature. So you see that Planck, being a physics, is absolutely abstract from the physical entity, okay? Provided their existence and their property are consistent with the law of the thermodynamic and electrodynamics. So you see that, as already said, Planck have already in mind the thermodynamic law, and as well as electrodynamic, because thermodynamic was well established since 1865. Electrodynamic was established since 1875 after Maxwell. Okay. If for a special arbitrary assumption regarding the nature and the arrangement of the emitting and absorption system, we can find the state of radiation in the surrounding vacuum, which is distinguished by absolute stability. So it means that he considers that there are a stability. Stability means that in the meaning of Planck means that the spectrum of this radiation don't change, no? Because in principle you may imagine that if you have the black body, so with inside the oscillator, and this is your electromagnetic radiation, you may think that if you put here the frequency, here the power, the electromagnetic oscillator, there are no way, because there should be no flat. But after some time that reaches the equilibrium, this spectrum reach another distribution. That was the typical distribution measured by the people at that time, or seen by Kirchhoff. Okay, Kirchhoff distribution. So he said the important is that the state of this distribution, okay, is stable. You see, it's gain absolute stability, which state can be no other. This state is very stable, could be no other that of the black radiation. In other terms, there are no other possibility to this state than to be this one, okay? And further on, he continues, since according to this law, we are free to choose any system, whatever, we all now select from all the possible emitting and absorbing system the simplest conceivable one, namely one consisting of a large number of n of similar stationary oscillators. Okay, so you see that Planck used a very generic approach to solve the problem of the black body. And he considered n similar or equivalent oscillators that are still stationary in a stationary electromagnetic field. Then what Planck do, you see, continue. Let the state of such an oscillator be completely determined by its moment, F, that he called a moment Ft, that is by the product, the electric charge of the pole situated on the positive side of the axis and the pole distance. This give, you know, so it means that you have here a charge, okay, so you have a sort of oscillator like this one, that is a dipole, electrical dipole. Okay, this distance time the charge give you the electrical dipole, that is the product of the electrical charge of the pole situated in the positive axis of the pole distance, and by the derivative of Ft with respect to the time. The derivative means that you consider the dynamical part of this. So this function, since this function is d charge, could be considered a sort of x, sort of distance, no? Because this one is the distance, like in the spring mass system. While the derivative of this distance gives the velocity. And you see that here, just compare the kinetic energy and the potential energy that we already seen in the mass spring. So the model of Planck is exactly this model. That is not different from the model of that will be developed after Planck. Because this Planck wrote this page in the 1900, but the model that Planck have in mind is absolutely the model mass spring, no different. Is sum and kinetic energy with potential energy, exactly like before. Okay, but So let the energy of the oscillator be U. So U is the sum of kinetic energy plus potential energy, where K and L denote a positive constant. So it's influence, which depends on the nature of the oscillator, but that need not be discussed at this point. So he's not interested to enter in the detail of this dipole or of this mass spring system. It's easy to see a parallel between the above energy and also the spring Mach system of the harmonic oscillator. Even for Planck, the pulsation of the oscillator is the square root of T divided R, exactly like a Planck mass system. Okay, this was the hypothesis of Planck. And then he put all these dipole, or if you prefer, mass spring, because it's the same object, in this cavity, closed, no, and isolated from the external environment. A cavity closed and isolated means adiabatic. Adiabatics because they don't exchange energy with the remaining part of the environment. Okay, so this adiabatic cavity realize a black body. So what is a black body? A collection of the Planck oscillator immersed in the electromagnetic radiation inside a vessel with a adiabatic wall and in stationary condition. Okay, this is the black body. Do you understand? You have a question about? Yes.
What does it mean, stationarity condition?
No.
I understood the graph, but
Yeah.
the physical meaning of
Stationary condition, I said already that is a word taken from the thermodynamic theory. It's not a generic word, but it's a specific condition that assumes two systems. So when you have a system in thermodynamics, no, and you put this system in contact, so you suppose a reservoir, some vessel containing some gas at different temperature, no, and you put this reservoir or this vessel against another reservoir, what happens? If the temperature are different, they exchange energy in order to reach the same temperature, no? Or if the pressure is different, they exchange pressure in order to reach the same pressure. Or if the potential chemistry is different, it exchange energy in order to reach the same potential energy. This occurs in p-n junction, for example, where the P semiconductor exchange energy with the N semiconductor in order to reach the same Fermi level. Okay? So this means that any time that you wait some time in order for the system to put in equilibrium. It's possible to demonstrate that this point of equilibrium is the point that maximizes the entropy function. So the entropy increases and the system goes to the stationary condition. When you arrive to the maximum entropy, the system is stable, because in the time you have no further evolution. This means stationary.
so there isn't an exchange between potential and
No, the exchange between the potential and the kinetic energy occurs in the oscillator. This occurs any time. It's a continuous exchange because the oscillator oscillates at the pulsation omega. So they are continuous. But this is, you suppose that one oscillator, the oscillator absorbs and emits continuously this electromagnetic energy. So the equilibrium of the stationary state is between the oscillator and the electromagnetic radiation inside the vessel. So it's not inside the oscillator, but it's among the collection of oscillator and the electromagnetic radiation inside the vessel. So, do you understand? So you have other question about so this is a model of the black body. Now what happened? the question is, since this black body is put at a certain temperature T, and already has been demonstrated by Kirchhoff, Vienne, and many other scientists that the spectrum of this black body is only dependent on the temperature T. So don't depend on the specific material that you use or system that you consider. The question is, what is the electromagnetic energy which affects my receiver? Why this question? Because when you have a receiver, whatever be the receiver, an antenna or in the space, or an antenna for the longer radio wave, or a photo receiver in the optical domain, okay, you may suppose that this receiver is embedded, this receiver, inside a giant, a huge black body, okay? So you have a giant black body where you insert your receiver. So the question, in other terms, is you suppose to have a front end, like this front end. I picture for you three typical front end: the photodiode front end, the radar front end, and the radio front end, okay? Radio front end is the front end of your smartphone, okay? The radar front end is the typical of the radar receiver, okay? The photodiode is pertinent to the optical communication. So if you have this three front end, the question is, what is the noise that affects the front end? So you may say, but this, I don't see the black body here in this schematic, no? But you have to imagine that the black body could be all the world around this front end. So if you front end put in this room, the black body is all the room. Or is the environment of the metropolitan area, or is the universe, okay? So, in other terms, the black body is absolutely a general concept that is not a concept that is restricted as a dimension, but you may consider a large, very large black body. Because people said that any time we have a temperature, we have emission of radiation, okay? So this is, I admit that this abstraction is this step is not so obvious, because the black body, people imagine some pot, okay, with very, very, very contained in a small wall, okay, heated with the flame or burner, but you have to imagine a more abstract concept of the black body. Okay, so the question is, in order to answer to this question, I have to study the black body radiation, because if I don't study, if I don't know the law of the black body radiation, I don't know the law of the radiation that impact on my receiver. I don't know if I am being clear in this explanation. So there are some point in this physical point that is critical. Okay, so you have to think oscillator, harmonic oscillator, so elementary oscillator abstract. Then you see that oscillator emit and absorb radiation with a law that we don't know at the moment. Okay, the law of absorption emission radiation we discovered after this theory. Because Planck said, it's irrelevant. Because Planck considered a thermodynamic approach, so it's irrelevant to know exactly what happened in the oscillator, okay? But what he says is important that oscillators are in thermodynamic equilibrium, that in other terms, emitting and radiation occur, and the sum of this emission and absorption process is a picture of my spectrum. And this is in equilibrium. Then people abstract further this model, okay, and they said whatever environment, not 0 Kelvin, not at zero temperature, is an environment that in principle contains oscillator. Okay, even in this environment we have oscillator, no? Because in this metal we have oscillator, in the wall I have oscillator, in my body is contain oscillator, and so we are in equilibrium in this room. Okay, because we continue to emit and absorb radiation in whatever spectrum, okay, in whatever spectrum range. So this continuous and absorption and emission of radiation is a sort of realized sort of black body, okay. So you see that the concept of the body is absolutely large. You have not to restrict the concept, okay? Do you have a question about this point? Because there are some conceptual passages in this story that I admit is not so obvious. Okay, if you have no specific question, we enter in some detail. So, since the container is warm, the terminal agitation lead to a balance between the radiation emitted and absorbed by oscillator. At the equilibrium, the probability of finding an oscillator excited at energy En go like the Boltzmann factor. That is, there are some probabilities that you find the oscillator excited in whatever one of this energy level, because because Planck introduces some discrete state of oscillator. So Planck said that the oscillator could not reach a continuum of state, but reach an En state that we already see is 0, 1, 2, 3, 4, 5. So these are all the possible exciting state of the oscillator. So there are some probability Pn that the state En is of the oscillator is excited. This probability go like the Boltzmann factor. This Boltzmann factor was already given by, in the denominator I have a normalization factor. What is a normalization factor? Is the sum of all the possible Boltzmann factors. Okay, this normalization factor is very important in the theory. It is called partition function. So the partition function is the sum of all the probability. Of course, this is a normalization of the probability, because the probability could range from 0 to 1. Okay, this factor minus En over Kt is a typical factor already discovered and known at the time of Planck by Boltzmann, because he said if you have an excited state and an average temperature T, you have a Kt, where K is the Boltzmann constant, given in Joule over Kelvin minus 1, 138, 10 to minus 23 Joule is energy over temperature. If you multiply K, this Boltzmann constant, okay, time T capital, you obtain Joule, that is, you obtain energy. Okay, so this probability is, give you an idea, since this exponential go with minus En, you see, since the exponential go like minus En, with this minus, so this means that if the energy increase with respect to Kt, the probability decrease exponentially. Or if the energy go to closer to 1 or less than go closer to Kt or less than Kt, the probability increase much more. Okay. this probability should be normalized by this term, okay, by this sum. So probability give a number but should be normalized. Okay. So you see that the probability range in function of the energy of the oscillator. Then we know by Planck that En could be whatever energy, but Planck said En is a discrete energy. This was the introduction of Planck, so the assumption or the hypothesis of the working hypothesis of Planck. This is because he break the classical physics, because Planck said En is not a continuous, but is stepped like this throw in terms of n that today we know in the present theory is energy of the photon. Okay, but at the time of Planck, this was not very known, of course, now because it was introduced for the first time by Planck. This H-Ni, he introduced H-Ni. Okay, so this was the Planck importance. Okay, so for the first time he said that the energy, electromagnetic energy in equilibrium with my oscillator is not a continuum of energy, but is discrete. So, okay, you have a question about this age? Because this is a theoretical, very important theoretical passage. It was the Planck original contributor to the physics of the black body. You see that this introduction, this NIC H omega is compatible with what we say survey, with the quantization of the electromagnetic field. Apart the term 1/2 H that Planck don't consider. So is absolutely today vision, the modern vision, no? Because apart the term alpha photon that the Planck don't consider in the 1900, this vision is the modern vision. Do you have a question about? Okay, then what happened? Since the sum is a geometric series and the exponential is negative, the sum converges to 1/1 minus E minus H omega divided Kt. So the probability is this one term. It's E minus N H omega, so instead of putting An, I put a minus H omega divided Kt, time 1 minus the same term H, okay? Because this series is a convergent series, it is called geometrical series, okay? Then what happened? So this is mathematics. Then Planck said, let me evaluate the number, okay, of the oscillator excited at the energy En. This number oscillator is NPN sum by the definition of average, no? Because this is a definition of average. When you have a probability distribution of an event and you have the event itself, the average is by definition sum NPN. Okay, so you apply the same definition of average. So this what the difference here is the meaning of this average. This average is should be interpreted as the number of oscillators excited at the temperature An when the black body is set in equilibrium at the temperature capital T. Okay. So since it is in average, we may write this with the bracket, angular bracket parenthesis, typical of the average. And this bracket parenthesis means how many harmonic oscillators with energy En are excited at the temperature capital T. Okay, you agree? Very simple. So there are no in quantum mechanics, the mathematics is very simple. What is difficult is the concept, you know, the mathematics. Okay, now we consider this, and then what is a Ni, capital Ni, is the sum that we wrote before, this one. But this term here, sorry, but I have not the pointer working. This term here is nothing more the derivative with respect to h omega over kt, is of the exponential of this sum. So instead of writing this term, I'm writing this as derivative. Okay. Then I put some reorganization of the term. Okay. And we obtain the derivative of this one is this one, by definition of derivative, times this. And I can say this with these two, it's just remain this factor here. So this factor represents the average number of oscillators excited. Okay. So it's very simple algebra, no integral. If we organize this factor, because I divide over the numerator and the denominator by this term, okay, we obtain this very simple expression. 1 over, sorry because the bar of fraction don't appear, but it's 1 over h omega over kt minus 1. So this one is 1 over h omega over kt minus 1. Okay, you see. This, I'm sorry because the parenthesis of the n does not appear and this does not appear. So this term is very important. It was the concept given by Planck in the black body theory. And it's called Planck factor. Okay. Why is so important? Because in order to obtain this term, you needed the introduction of the quantization of the field. Otherwise, you have not the sum that converge as a geometrical sum. Okay, so this is important. This term is called Planck function or Bose-Einstein factor because it was reobtained by Bose, that was an Indian scientist, and by Einstein some time after. Okay, and this function is the more relevant function in all the electromagnetic theory and in the light theory. You see that it's a very strange function because this function presents a denominator which go very quickly to 0, okay, if this exponential go to 1. Then it means that when the exponential go to 1, this go to infinite. Why? If the energy of the oscillator increase and increase, this function go to 0. So it's a sort of hyperbolic function. You remind hyperbolic. Okay, it's the classical hyperbolic function that go like this. Okay. So it means, let me read this function, it's very important. When the pulsation go to low frequency, because in the horizontal axis we have a pulsation. No, because we have a, if we fix the temperature, like a temperature of this room, okay, the temperature in this room is 20 degree, to suppose. Okay, so it means that T is 273 plus 20. Okay, so 293. This is a number. Okay. Then you multiply this number by the Boltzmann constant, so you have the denominator a constant because Kt is a constant given certain temperature. So what you move in the horizontal axis, the variable in the horizontal axis is only the frequency. Frequency of what? Of the harmonic oscillator. But in this case it corresponded to the frequency of the specific electromagnetic radiation considered. So in this frequency means that you have excited the harmonic oscillator, and the vertical scale give you an idea of what is the number of oscillators contained in your black body that are excited. Okay, so that means that if you, what means this? Another term, read this function, help me to read this function. Is there more excited oscillator at low temperature or high temperature? If you change the temperature. Or in other terms, if you fix you suppose to fix the temperature, okay? Now, in this room, we are in this room, 23 degrees, and you consider that this room is your black body, okay? Is there more probability to have a low frequency excited oscillator or high frequency in this room? Low or high frequency? It's not a terrific question. Eh? Low frequency, you say. Okay, you? Eh? High frequency, and you said low, so you have to decide. Why they say the high? Look at this function, please. In the denominator and the vertical scale, the meaning. So the axis scale, because the k is a constant, because it's Boltzmann constant. So it's 10 to minus. K is 138, 10 to minus 33 Joule Kelvin. Okay, this is a constant. Now T, I decided that is a constant. Okay, so you suppose that T is 23 degrees centigrade. Okay, so that means this is the T is in Kelvin. Okay, so that means that T is always 273 plus temperature in Celsius. So this means it's 273 plus 20. So it means 293. Okay, this is a constant too, because in this environment it's very difficult to change the temperature in this moment, in few seconds. So we are in equilibrium in this environment now, okay? You agree? It's difficult that the temperature move now, okay? So the temperature here is 293, if you agree. Kelvin, yes, in Kelvin, because the temperature is always measured in Kelvin. We use Celsius because conventional, because some story, but it's not, it's never measured in Celsius, okay? It's always measured in Kelvin, the temperature, okay? So temperature is 293, so it's around 300 Kelvin, no? Why? K is a constant, so it means that Kt, okay, is 293 times 138, 10 to minus 33 what? Joule. So this means if somebody make for me this multiplication, 293, 138, you make a multiplication. When you make a multiplication, yeah, you have no, okay, thank you. 404, 34, okay, it's about 400, okay, 10 to minus 23, okay, joule. Okay, so this is the key. Could be of interest, no? Could be of interest if we express kT in terms of another unit of measure that already met. We already met another very useful unit of measure for the light. You remind, the photon of the light is measured in what unit of measure? Electron volt, right? So let me express this in electron volt. 1 electron volt is 1/6 to minus 19 joule. Okay? So this means that 400 10 to minus 13, okay, divide 1/6 10 to minus 19 is approximately, so divide for me 1.6. 250, okay, is 250, okay, 10 to minus 4, okay, because it's 10 to minus 33, 10 to 19, okay, so it's 10 to minus 4. So this means 25, 10 to minus 3 watt electron volt. You agree? Because now this is electron volt, because I divide. Anybody follow me? Very simple. So please, this means 25, 10 to minus 3 electron volt. You agree? Let me call this 25 milli electron volt. Milli because it's 10 to minus 3. You agree? Not so. Okay. Okay, please stamp in your mind this number. Stamp here. Okay? Collect in your mind this number now. Because when you move, you have to compare with this number, 25 milli electron volt. Is it this number larger or smaller than the typical energy of the photon? Do you remind the energy of the photon in 1.5? We evaluated many times, at least 10 times this number. Do you remind?
0.8.
0.8. So 0.8 is larger or smaller than this number? Much more large, not large, much more larger. So this means that this number is very small. So this means that if I put here the energy of the photon, okay, what number I have to put in this scale, in this graph? Let me try. 0.8 divide 25, 10 to minus 3. Please. Watt. There are some exponents here. 0.8 divided 25. 0.032. 0.032, 10 to 3. You agree? Okay, so it means 32 times. So this means that if I put this number, this is the exponential. This one, what I evaluate in this number here, what is this number? Is H omega bar divide KT. You agree or no? You agree or no?
32 is a constant or?
No, the number that you evaluate, 32, is exactly H omega divided KT. You agree or no? Because we are in electron volt as unit of measure. 0.8 you said is in electron volt, 25 is in electron volt. So we are okay as unit of measure. So this is exactly what? The exponential of this function. So it's this denominator. It's this axis. So this means that if I consider a photon inside this room, okay, at the temperature, this scale 32. So you have to open the door and go outside and move far away. So this means that this is a probability to have a photon in this room excited. But please, this is a room 32. Then suppose to switch the light and to close the window. Make this after the experiment. Close the window. Okay. Then switch the light. Okay. Then switch the projector. Do the temperature change? Temperature change? No or yes?
No.
Temperature change? No. So this means that you are in a bath. So like a warm bath, we stay inside. Now, if I close the window and switch this projector, we are in the black room. You agree? So this black room is a black body, in effect. So this means that the probability to have a photon excited is 10 to minus 32. So it's not 10 to minus 4, it's 1 over e to 32 minus 1. So it's around, this number is, you may consider, is around e minus 32. Because this is the number of oscillator excited here, in this room. So, exponential minus 32 is a big number or small number? No, it's not small, it's very small. It's very, very small. So, probability to have excited photon inside this room is 0. So this means that with a bath, you cannot excite photon. And this is agree with our experience because light came from hot body, not from warm body. You agree? So there are no photon in this room, in other terms, at 273 degrees Kelvin. And this is what Planck factor said. This is not a Planck function. This is a Planck factor. Okay? So this means that this probability is absolutely very, very low. The probability to have excited photon. What I have to do in order to increase this probability? I have to move to lower frequency. If I move to megahertz, okay, then not to terahertz, but to megahertz, 10 to 6. If I scale 10 to 6, okay, this number of energy here in the numerator, okay, this number became 10 to 6 higher. So this means that if I scale this, in effect, the probability to have a megahertz frequency inside here is absolutely very high. And in effect, this is why your cellular phone is protected by the low frequency noise. Because if you switch on this phone without a protection of electromagnetic noise, we hear noise. because you are always inserting this noise. This noise is emitted by the wall, by the ceiling, by whatever object here. Okay? So this means why this function is so important, because the function rule all the noise that affect whatever device. Okay. So this means that when you have our optical front end exposed, okay, we have no problem in photon, because if you switch the light, there are no photon noise, but you have electromagnetic noise. The electromagnetic noise moves a charge in the wire and gives the Johnson noise. This is why the only noise that we have in a room temperature is electrical noise, that is a Johnson noise. Okay, so this gives you an idea of this N, okay, a different thing. So you see that N at 10 to 14 is 1.2 10 to minus 14. That is this one. Okay? So probability is very, very small, 10 to minus 14. Why? If you have a radio wave with the wavelength of 1 meter and the frequency of about 300 megahertz, the probability is 10 to 4. So in this room, okay, we have no photon excited if we, of course, close the window and switch the light. That is, if we close the hot thermal source. But we may have a very high probability, 10,000 of oscillator excited at 10 megahertz or 100 megahertz of frequency. Why? If we move 30 gigahertz, we have 2 10 to 2, so 200. And we go to your smartphone antenna is a 2G. So if you 2G is in between these two numbers. So maybe that there are at 2G, this is 30G. So maybe that 2G is higher. So you may be 1,000 of oscillator impacting on your smartphone at room temperature. If you want to decrease the noise affecting your smartphone, what you have to do, you have to cool this room temperature. Maybe you may open the door in the winter, okay? Or go inside some refrigerator. If you put this cellular in the refrigerator, the noise affecting the cellular decrease. Of course, if you put this in a nitrogen liquid, it decreases more. If you put in helium liquid, it decreases even more and break. Okay. But any time, this is just fun to give you, remember this table. So there are no chance for the optical photon to be excited at a regular temperature. Okay? So there are no any possibility. Now my smartphone has been excited by some radio wave signal, but not by noise, okay? Because it's filtered by noise. Okay, so it's why all the radio receiver are filtered at low frequency, are filtered in order to avoid the capture of this noise. So you see that the black body concept is not abstract concept, it's very practical concept. But of course you have to put a number inside the expression, as always, okay? Always put number, okay, because otherwise you don't understand anything. You follow me? Okay, just a break a moment here.